Hello class. Today we're going to do section 5.5, the substitution rule. Before I go into any of the rules, what I want to do is show you an example so you guys can kind of see what the idea behind all of this is. So the first thing that we're going to do is we have a product here, and this product, we have the 2x and then the root of 1 plus x squared. And I've talked about that before where we didn't know how to do that. Well, I'm going to show you a method to try to deal with that today, and that is the substitution method. I'm going to try to get rid of the 2x and the dx by doing a substitution. And the way I'm going to do the substitution is I'm going to take the inner function, which is u is equal to 1 plus x squared, and then I'm going to take its derivative. So I'm going to get du is equal to 2x dx. And now we see that the highlighted part is exactly what's on the right for the du. And then I'm going to do the substitution. So now my integral is going to be the integral of the square root of u du. This is exactly the same thing as the problem that we have in terms of u. So when I take the integral of this thing's really going to be u to the 1/2 du. And when I take the integral, I'm going to get 2/3 u to the 3/2 plus c, and that's because it's an indeterminate. But we need this to be in terms of x, and so when we have it in terms of x, I need that u to become back in terms of x. So I'm going to get 2/3 1 plus x squared to the 3/2 power plus c. This is our answer in terms of x. Okay, so there's two rules that we have. It's the substitution rule for indefinites, and when we do it for indefinites, I'm going to use a different color. My du is going to be representative of the g prime dx. And this should be a g right here. Let me fix that. The g of x, this piece, is really my u. So my u will be the function of the innermost part of some composition function. Okay? And then when we have a definite integral with an upper and lower bound, notice what happens to my a. If we keep everything in terms of u and we don't change it back, what ends up happening is it becomes the a becomes g of a, or the substitution for our new u function, right? Our upper bound, b, becomes g of b because it gets evaluated into b. So I'm going to show you how to do that in this next example, just so you guys can kind of see it. So in this example, the inner function is going to be u is equal to 4 plus 3x. And so when I take the derivative, I'm going to get 3 dx. But I only want dx, so I'm going to divide by 3. So I'm going to get 1/3 du is equal to dx. Now when I go to the integral, I'm going to go 1/3 in front. The square root of u du. But my upper and lower bounds need to be changed. So to do that, when x was 0, my u is going to become 4 plus 3 times 0, which is going to give me u is 4. So my lower bound will be 4. My upper bound then is when x is equal to 7. So I'm going to go u is equal to 4 plus 3 times 7, which is going to give me 21 plus 4, which gives me 25. So my upper bound is 25. Now, when I do this, then I'm going to get 1/3. This becomes u to the 3/2 times 2/3, correct? And it's going to be evaluated from 4 to 25. And so what I'm going to get is 2/9, and I'm going to get 25 to the 2/3, oops, not 2/3, 3/2, minus 4 to the 3/2, which is going to be 2/9, 5 to the 3rd minus 2 to the 3rd, and the reason that is, just so you guys know, it's 5 squared to the 3/2 minus 2 squared to the 3/2, and so when you multiply those, the 2's would cancel. So then that's going to give me 2/9 times the quantity of 125 minus 8, which will give me 234 over 9, which simplifies to 69. Oh, 69. Simplifies to 26. I don't know why I thought that. That's funny. Okay. Geez. So the answer to this problem is 26. Okay. Now for trigonometric functions, we can also do it. And so in this problem, we don't know how to do tangent of x. So what we're going to do is we're going to change that to be the integral of sine of x over cosine of x dx. And so here, typically with the u, it's either the inner function or the denominator that we use for u. So I'm going to make my denominator my u. And the derivative of cosine is negative sine of x dx. And so we can see that that's going to give us sine dx, but it's got a negative, so then that means I'm going to get negative integral of 1 over u du, because we need the negative piece because of the negative, and then the sine dx become du. And then from here, I know that the integral of 1 over u is ln, so I'm going to get negative ln of u, oops, negative ln of u, plus some constant c, but again, we don't want it in terms of, u, so I'm going to go negative ln of cosine of x, and really we could do absolute value. We probably should do it just to be consistent. Now remember that negative in front is like a power, so that would make it ln of secant of x plus c. Now just so you guys know, I will accept either one of these answers. A lot of people forget about the negative in front being an exponent when we're doing with logs, but that's something important to understand. Okay, now this next part is really kind of cool. If we have symmetry, and there's two types of symmetry, there's odd and even, and I wrote down those rules so you guys can check them, because I wanted you guys to have them, and note that that's negative on that one, negative f of x. If it's even, what ends up happening is you have a picture that looks like this. So in even, of course, I was going to use x squared, right? If this is negative a and this is a, the area that we end up finding under the curve for both of these is the same on the right as on the left. And so what I can do is instead I can just go 2 times the integral of f of x dx from 0 to a. Instead of doing the from one side to the other, I can use the symmetry as a tool and just deal with the right hand side. Now, if it's odd, what's cool is I'm going to use an odd function. So I use x squared for that one. Here is x cubed, and here's from negative a to a. And the one thing that we need to remember is when we're below the x-axis, this is a negative area. And when we're above the x-axis, it's a positive area. So those areas are the same but have different signs. And so because of that, we end up with an area of 0 total from negative a to a. So if you know that a function is symmetric and it's an odd function, we know that the area is going to be 0. So look at this example that we have here. We can think of it in pieces. So this denominator is even, right? That's even. X squared is even. And we know that sine of x is odd. So even times odd ends up being an odd. And so we know that this thing is going to be equal to 0. Please remember that. It's an important rule to know. Now, if you didn't know how to do it by just looking at it, I'm going to show you how to do it with the rule. And so the rule tells us that f of negative x is equal to negative f of x. That would make something odd. So looking at this problem, I'm going to go negative x squared sine of negative x over 1 plus negative x to the 6th. Well, doesn't that become x squared minus sine of x over 1 plus x to the 6th, which is negative x squared sine of x over 1 plus x to the 6th, and that is negative f of x, which makes it odd. And since it's odd, we know that the integral of a symmetric function is 0. Okay, cool. Now, one thing I want to do is I want to do a couple more examples just because, it's good to show you a bunch of examples. And so here are some examples for you to look at. So x to the 3rd cosine of x to the 4th plus 2 dx. The inner function of this, the furthest inner piece to this function, is x to the 4th plus 2. And so when I take the derivative of that innermost function, I'm going to get 4x third dx. Well, if I look at what I have x to the 3rd and I have dx. I don't have the 4, so I'm going to divide by 4 to the other side. And now I have what I need to match. So then when I do the integral, I'm going to go 1/4 the integral of cosine of u du. Do you see how this makes the problem so much easier for us to be able to integrate? We know the integral of cosine of u, so we're going to get 1/4 sine of u plus some constant c, because we don't have bounds, we're indefinite. But we don't want it in terms of u, we want it in terms of x. So I'm going to go 1/4 sine of x to the 4th plus c, x to the 4th plus 2 plus c. And so this is my solution. Okay? All right, let's try another one. So let's say that I gave you the integral of x over the square root of 1 minus 4x squared dx. We want the innermost piece, or the denominator, right? Well, in the denominator here, we have a square root and then a function inside. And so what we're going to do is we're going to take the inside of the square root. So I'm going to go u is equal to 1 minus 4x squared So my du is a negative 8x dx. Well, I have x in the denominator. I don't have the negative 8, so I'm going to divide by that. And now we see that we have those pieces taken care of. So I'm going to get a negative 1/8 integral of 1 over the square root of u du. Well, we can integrate this problem. So we're going to get a negative 1/8 integral of u to the negative 1/2 du. So that's going to be u to the 1/2 times 2 times a negative 1/8 plus c. But again, we don't want it in terms of u, so I'm going to get a negative 1/4. My u was 1 minus 4x squared. It's going to be to the half power plus some constant c. Okay, let me show you another one. Again, I just want to show you an example. And so in this example, I'm going to have the integral of e to the 5x dx. And in order to be able to do this problem, what we're going to do is I'm going to make my u the exponent. So then du is 5 dx. So 1/5 du is dx. So I'm going to get 1/5 the integral of e to the u du. We know the integral of e to the u is e to the u plus some constant c, but we need to multiply by the 1/5. We want our answer in terms of x, so it's going to be 1/5 e to the 5x plus c. There's our answer. Very cool. All right, let me do one more example for you, and then I want to go back and touch on a problem that I did earlier and show you another way to do it. Okay, so let's make it more complicated. So the integral of x to the e of x times e to the 7x squared dx. So again, we have a product here. What we're going to do is we're going to use the exponent as our u. And so I'm going to get 14x dx. But if we notice, it's x and dx that we're trying to do for our products. So I'm going to go 1 over 14 du is x dx. So we have that now. So I'm going to go 1 over 14 integral of e to the u du, which is going to give us 1 over 14 e to the u plus some constant c. And we know what our u is now, so it's going to be e to the 7x squared plus c is our answer. Okay, now one of the things, you know what? I got 2 more examples I want to do actually before before we go. I think they're good little tricks that are probably going to be useful for you to look at. Okay, so check this out. I want to do some definites. So e to the 1 over x squared dx. Now here in this example, in order to be able to do this problem, I'm going to use my u to be 1 over x. And the reason I'm going to do that is because I know the derivative of 1 over x is a negative 1 over x squared dx. And see what that does is when I multiply by that, that is the denominator of this problem. So I can rewrite this problem so you guys can clearly see what I'm doing. Is 1 over 2 e to the 1 over x times 1 over x squared dx. And we can see that that's this part, except for the negative. So I'm going to put a negative there, and I'm going to go the integral of e to the u du. Now, I'm going to do this problem in a different way. So instead of going back to that original problem I showed earlier, I'm just going to show it in this problem. Instead of changing the bounds, I'm going to change this back to in terms of x and then find the answer that way. So the integral there is going to be the integral of e to the u, right? But then I'm going to change that back to e to the 1 over x, and I'm going to evaluate it at the numbers that we were given. So notice I'm using 1 and 2 in terms of x once I changed it back to x. So that would give me negative e to the 1/2 minus, and I'll do it this way just so you can see it, minus, from the Fundamental Theorem of Calculus Part 1, e to the 1 over 1. And then that's going to be, with the negatives, I can rewrite it as e to the first minus e to the 1/2 power, right? And I'll just leave it in that form. Now, if I had decided to change the bounds, I could have done it, and I'll show you. So if I would have changed the bounds, when x was 1, I would have gotten u is 1 over 1, so u would have been 1. And when x was 2, I would have gotten u is equal to 1 over 2, so it would have been u is 1/2. Now, those bounds, and I'll write them in red so you can see that I'm doing it. The lower bound would have been 1. The upper bound would have been 1/2, right? And I'm not going to flip it. I'm just going to leave it that way so you can see it. I'd get 1 and 1/2. And so by doing that, I get negative the lower bound, the upper bound, e to the 1/2 minus e to the 1, which when we clean that up becomes e to the 1 minus e to the 1/2. So the whole point of me trying to show you this is if you want to change bounds, you can, but if you don't, just go back to terms of x and then evaluate with the original bounds that you had. You will get the same answer. Sometimes it's more work to change back to x's, but I just wanted to show it to you so you can have more than one way to be able to solve these problems. Okay, let's do one more example, and I want to do 2 more examples and then we'll call it a day. I keep adding examples, right? Okay, so if I do negative pi over 6 to pi over 6, that should already spark something in you. That's talking about symmetry. You should look at symmetry of tangent cubed of theta d theta. We know that tangent is odd and the power of it is odd. And since they're both odd, we know that this is going to have an answer of 0. And the reason this is because we have an odd function. Okay? All right. our last example. All right, tan. We're going to have integral of e to the tan of x times secant squared of x dx. And here in this product, since we have this, we're going to use the exponent as our u. So u is tan of x. The derivative of tan of x is secant squared of x. And so we're going to get the integral of e to the u du, which will give me the integral of e to the u plus some constant c. But we want that in terms of x. So I'm going to get e to the tan of x plus c. And that is our answer there. So with all of these problems, the trick is to try to find a u that will eliminate one of the products in our problems. How about I do one more example? I want to show you guys as many examples as I can. I think it'd be good for you guys to see. So let me just do one more. Sorry. Alright, so the integral of cosine of x sine of x to the 6th power dx. Now in this example, I'm going to use sine because it's an even function, because it's to an even power. I could have broken it up and done some things, but sine, the derivative of just sine, eliminates cosine, and so that's why I'm doing it. So that's going to get me cosine of x dx, and we can see that that gets rid of cosine and dx, so I'm going to get u to the 6th du. So then when I take the integral of that, I'm going to get u to the 7th over 7 plus c, and then that's going to be cosine, it's going to be sine of x to the 7th power over 7 plus c. So I've done a few examples for you now that should be very helpful for you guys in terms of moving forward. I will do a question and answer for you guys on this stuff, so don't get too worked up, but I wanted to have this recording for you guys so that I could exclusively focus on doing homework problems and examples for you during our class meeting. All right, I wish you all the best. Stay safe, stay healthy. Bye-bye.